This chapter is on immunization and immune testing. For this first mini lecture, we'll focus on the history and types of vaccines. In this chapter, we talk about the artificial methods of immunity, active immunization and passive immunization, which we've already discussed a little bit in previous chapters. First, some history of immunization. Back in the 12th century, the Chinese already had noticed that children who recovered from smallpox wouldn't get the infection again. They invented a practice that's called variolation. Variolation involved taking an individual who was recovering from smallpox, and smallpox gives you lesions on the skin which would scab over as you healed. And as a person was recovering, they would take the scabs and grind them up into a powder. Then they would have the person who is susceptible to smallpox inhale some of this. They didn't really understand what was happening, but they knew a mild infection usually resulted, and then the person would be immune to reinfection. We now know that what was happening was that within the powdered scab material would be damaged viruses because the immune system was attacking them. They probably had antibodies and complement bits stuck to them. That would allow the person to generate an immunity to the virus. Usually this practice caused a mild case of smallpox that the person could recover from, but sometimes it would actually lead to full-blown smallpox, and the person would succumb to the infection or be very, very sick and devastated by it. But overall, it had such a positive impact on people becoming immune that it was widespread, and the practice actually spread to England and America because the wife of a diplomat witnessed the practice in the region she was in and brought it back to England. However, it did stop because of the risk of death once there was something better that came along. That something better was the first real vaccine. You may have already heard the name Edward Jenner. He was the individual that discovered vaccination. Vaccination started with addressing smallpox, and the vaccine used related virus called cowpox in order to stimulate immunity to smallpox. What you can see here is that there are different vaccines being demonstrated. When they were introduced, the rate of infection plummeted in the United States. Once the polio vaccine, and there was actually 2 different versions of it that are still in use today, that incidence plummeted, and the same for measles as well. There are pockets of the population that refuses the measles vaccine, and we'll see some localized outbreaks that have occurred here and there. This is a very contagious virus, and the infection still exists in region of the world, so periodic transmissions occur which can seed outbreaks. We'll talk more specifically about this infection and the risks to those who acquire the infection later in the semester. But overall, you can see that the infection rate has drastically decreased because of the widespread availability of vaccination against this infection. As you recall from an earlier presentation, when we use active immunization, we're trying to stimulate the person's immune system to respond. We can do that in a couple of ways. One way is to use an attenuated live vaccine. A live vaccine is going to be a virus, typically, that is no longer completely virulent. The vaccine strain is very reduced in its ability to cause disease, but it can still cause a very mild infection. That will stimulate a very strong immune response. Importantly, you can get cell-mediated immunity because you actually have the virus going internal to the cells and starting that whole MHC1 presentation and stimulation of cytotoxic T cells. Additionally, often this can provide what's called contact immunity. That means that the person getting the attenuated virus is experiencing a very mild infection and has replicating viral strains occurring in that individual. When they come in close contact with somebody else, they can actually pass that vaccination strain to their contact, and that person can then become immune. This can actually be something very useful when you think about how some of the regions of the world where immunization is difficult. Therefore, you could vaccinate one person and that person can actually spread the vaccine strain to a few other people. That could increase your ability to vaccinate the population. However, this can also be a double-edged sword and be a problem. The first problem with contact immunity situation might be that the attenuated strain still might cause disease in some individuals, especially individuals that are immunocompromised. People with weakened immune systems may not be able to effectively rid themselves of a virus that typically causes a mild infection. The second problem is if the attenuated strain is able to mutate in such a way that the pathogen recovers full virulence. This has happened a few times in the past and is something that really has to be guarded against. It's especially true for the polio vaccine. For the attenuated polio vaccine, there has been documented cases of it reverting back to wild-type strain and causing full-blown infection. Recently, in the Philippines, the vaccine strain has been passing around via contact transmission for so long that there has been an accumulation of mutations that allowed it to become more virulent once again. If you vaccinate one person, but very, very few other people are vaccinated, they spread that strain to contacts, and the contacts spread it to other contacts, and so on. That strain starts to mutate, and it passes again to more people, and eventually it can recover its virulence. That is, in fact, what is happening in the Philippines, and it's causing a huge problem. So what's the solution to that? The solution is to vaccinate more people with the attenuated strain so that prolonged contact transmission type of virus passing cannot occur. Vaccinating more individuals will halt the transmission and thus the outbreak. The problems associated with attenuated polio vaccine in the past is the reason why the United States doesn't use the attenuated strain much anymore. They've moved to a killed version of the vaccine. When you're using a killed vaccine, then what's involved? The vaccine may have the whole agent that's killed. Basically, you take something like a bacterial strain that's normally infectious, kill it, and then use it as a vaccine. That often has some side effects associated with it. Think about all those cell components like LPS and other PAMPs, or factors that might be toxic to specific cells in a whole agent vaccine. Sometimes we see frequent unpleasant side effects. Whole agent vaccines are not a version that is often desirable, especially for things as complex as bacteria with many, many components. With modern technologies and genetic engineering, vaccines have evolved into a more specific type of immune stimulator. A subunit vaccine is now more often employed, meaning that you're only going to take specific proteins or specific antigens from that pathogen and use it in a vaccine. That approach is going to be safer than live vaccines as well as whole agent vaccines because you're choosing which protective antigens you want to include. But there are disadvantages to this approach as well. When you use only subunits, you're not giving the individual as many antigenic molecules to stimulate the immune response. You're only giving them a subset. Often, that means you're going to have to give booster doses in order to increase the response. When you're using attenuated vaccine, you often do not need another dose in order to get a very strong protective response. But it's pretty much universally true that when you're using a subunit vaccine, you're gonna have to give booster doses to boost the immune system to have a strong enough response to be protective against the real pathogen. The other thing that can be used to boost an immune response is the use of what's called adjuvants. Adjuvants increase the effectiveness of an antigen's ability to stimulate immunity. Adjuvants are used with toxoid and subunit vaccines. We'll talk about toxoid vaccines in just one moment. But what exactly are adjuvants? You can think of adjuvants as a way to prolong the exposure of your immune response. Think of them almost like a slow release capsule of some sort of drug. What you're doing is you're making little vesicles, little micelles of the vaccine component, and you're injecting that. Your immune response clears these over a longer period of time compared to antigen alone. They take more time to clear from your system compared to the all-at-once exposure and clearance of antigen without adjuvant. Therefore, you end up stimulating your immune response over a longer period of time, which allows your immune system to ramp up in response and respond more strongly. That's what an adjuvant does. So what's a toxoid? A toxoid, as the name sounds, is a modified toxin. Obviously, you don't want to give a toxin because you'd have a very negative effect on the exposed individual. If you need an immune response to a toxin, you can modify the toxin, usually with heat or a chemical, in order to make the toxin lose its toxic effect but retain its antigenicity. Some epitopes will be retained that will be protective once you respond to it. Toxoid vaccines really only are going to enable an antibody-mediated immunity, which is fine because when you're thinking about something like a toxin, we really want antibodies to neutralize the effect of that toxin. If it's neutralized, the toxin can't bind to its receptor on the cell and initiate whatever toxic effect that toxin would have. We're trying to stimulate antibodies to neutralize the toxin should you come in contact with it. But again, because we're giving basically one molecule with a limited number of epitopes that are going to be protective, we're going to have to give booster doses. We're going to have to show the immune response this particular toxoid several times in order to generate a high enough concentration of antibodies in the blood to actually be neutralizing should you come in contact with the real deal. When we're immunizing, we can have different types of vaccines, and we can see this with the COVID-19 vaccines. That vaccines that are effective against the SARS-CoV-2 virus come in different varieties. They all are the product of genetic engineering, and none are the strictly attenuated or inactivated whole virus. I'll revisit this topic in a moment. But first, what kinds of vaccines are there? First, we have a combination vaccine where we're going to combine antigens from several different pathogens in order to give just one shot and protect against multiple things. You see this when we're thinking about vaccines that we probably all had, hopefully have all had, like the MMR, measles, mumps, and rubella, and the DTaP or Tdap, depending on what version of the vaccine you've got, which is against diphtheria, tetanus, and pertussis, which is whooping cough. So these are combination vaccines where we're going to combine several different antigenic components from several different types of pathogens and give one shot to protect against multiple diseases. We know that some of the vaccine makers are developing a COVID and influenza or flu vaccine. The other types of vaccines definitely use recombinant gene therapies. Researchers try to make vaccines even more effective, cheaper, and safer by isolating the specific component that we're trying to generate antibodies to, and then we're going to only expose the immune response to those particular antigens to reduce the risk of negative effects. Then we have a new version of vaccine in use now. While there had been other work before, nothing had been in widespread use before the current anti-SARS-CoV-2, the COVID-19 vaccine. Now, some of the versions of the vaccines are using messenger RNA, the genes that we want to express and respond to. Other versions of the COVID-19 vaccines may become available, but the front runners will likely be dominant for some time, as now millions have been vaccinated with very few documentations of any adverse effect that can be linked to the vaccines. I'm going to return back to this image that we've looked at before to re-explain what the recombinant vaccines can be composed of. So we're using genetic engineering in order to allow us to make different types of vaccines against COVID-19. This is true of pretty much any infectious disease. We're just using this as our example because it's something we can relate to well since we have a lived experience with this pandemic. Since we're dealing with a virus that is an RNA genome, the first thing that we have to do is isolate that RNA and then make it into DNA. We would use our reverse transcriptase and do a PCR reaction to amplify up the genes that we're specifically interested in, like the spike proteins used by the virus for attachment to our cells with ACE2 receptors. We could block the ability of the virus to attach and initiate infection if we stimulated neutralizing antibodies to the viral spike protein. That's the goal. This would be a good gene to use, and they are using as a vaccine. They'd amplify up the gene that they're interested in, so now they have DNA. Then they put the DNA into the vector. So in this case, it's some sort of plasmid vector. We know that we're going to have to use the tools of genetic engineering, of biotechnology, to clip off the ends of the PCR product and open up the vector with the same restriction enzymes, and then use ligase to glue the viral gene, the PCR product, into our vector. So what could we do with that vector? Well, we put it into E. coli. We transform E. coli and then have E. coli make multiple copies of the vector as the culture is growing. We can have lots and lots of DNA as a product. We can also have the E. coli express, meaning make the protein from the vector. What we can see over in the last column, what we can do, we can have the purified viral proteins by having the E. coli make, right? Transcribe and translate the viral gene. Additionally, we can also use the message itself as a vaccine component. The idea behind that is to have our cells take up the message and translate the message within our cells. That's going to stimulate cell-mediated immunity because our immune system is seeing the cells make a viral protein and they believe it to be an infected cell. It's definitely altered. It's taking up that messenger RNA, and so then the cell-mediated immunity is stimulated. The mRNA would only have to get as far as the cytoplasm of our cells in order to work. One type of COVID-19 vaccine is mRNA. Those are the well-known Moderna and Pfizer versions that are being used currently. But theoretically, at least, we can back up even further. Some viral vaccine candidates are DNA molecules. They are putting the vector with the viral gene into the cells. They're injecting that, and then it's taken up by our cells. It would have to make it all the way to the nucleus so that it could be transcribed into message and then translated in the cytoplasm into viral proteins. The more classic type of recombinant vaccine is just purified protein. You will have a cell like E. coli make the protein from instructions on a recombinant plasmid, you purify the protein, and you give that as the vaccine. But another vaccine type would be a recombinant attenuated virus. So a blend of the older version of attenuated virus, but take a weakened virus and insert the gene from a pathogen that you want to stimulate immunity. The Johnson & Johnson and some of the other COVID-19 vaccines in use took this approach. They took a weakened virus that cannot cause a full-blown infection and inserted a spike protein gene in it. So again, you have the ability to stimulate a cytotoxic immune response to the spike protein because of the attenuated virus causing a very mild infection in vaccinated individuals. We can see that presently we have quite a few different types of vaccines that are possible. Even considering just one important disease, COVID-19, we can see there are several types of vaccines being tested or in use already. Importantly, all the newer vaccines are recombinant types of vaccines that employ the tools of biotechnology in order to more precisely stimulate the immune system and generate protection. This will conclude our first mini lecture of Chapter 17. See you in Part 2.